Hi, so I'm going to do section 1.3 of the notes, which is all about addition, subtraction, multiplication, division. I guess it's kind of related to the algebraic structure. Of the complex numbers. I've been implicitly assuming that you know how to add, subtract, multiply, not divide, but at least to add, subtract and multiply complex numbers, and that's not exactly fair, so we're going to work through it in detail, and you'll see all the same kind of structures as this in the group theory section. Right, so we're going to go through everything in detail. It reinforces the group theory side of things as well, so it's worthwhile doing, and hopefully you'll see where I've been cheating things a little. Okay. Addition. Now we've basically been done this a little bit, I think, already. So given z equal to x plus iy inside the complex numbers, given z and w equal to u plus iv, both in the complex numbers, we define z plus w to be equal to x plus u plus I times y plus v. Okay, in particular, the real part of z plus w is equal to x plus u, and the imaginary part of z plus w is equal to y plus v. Alright, two examples from the notes. 33 plus 4i plus 1 plus 4i, 34 plus 8i, and 82 plus 6i plus minus 8 plus 4i is equal to 74 plus 10i. So just as it shows here with the imaginary and real parts, you just add the imaginary and real parts separately. Okay, so we can draw a nice little picture of this. X plus onto u v add onto y z plus w. Okay, so the interesting thing to note about this is if you happen to have seen addition of vectors, then this behaves the same way. We've taken this bit and we just added it on. Or you've taken z and added it on to w. That's not a coincidence. The structure of the maths is the same. If you haven't seen those things, then don't worry about them. Okay. Okay, so exercise 1.3.1 wants you to do addition and to define what the relevant equation is when you have z equal to r cos theta plus I r sine theta, and w is equal to s cos phi plus is sine phi. Now, following the convention from previously, when you add these two together, you're going to get r cos theta plus s cos phi plus I times r sine theta plus s sine phi. Okay, now, so the real question is find RST, and this is a variation on phi, so find these two things, so that is equal to t cos phi plus I t sine phi. I mean, they exist, but what are they? It's a good exercise. I suggest you do it. There's a lot of work. Well, there's some work involved. Okay, so trig identities, right? Okay. Lemma 1.3.4. Okay, so for all z, so this is a symbol which in mathematics means for all. It comes up often enough that it's worth remembering, but probably not often enough that you need to care a great deal about it. I use it because it simplifies writing things down. Anyway, for all z in C, z plus the conjugate of z is equal to 2 times the real part of z. Right, so in particular, and this is an element of the real numbers. Proof, so take z, x plus iy, the complex conjugate is x minus iy, which is x plus I times minus y. So the y and the minus y are going to cancel. X plus, well, add the real parts, x plus x, 2x plus I, and then you add the imaginary parts, y plus negative y. Of course, that's equal to 0, so this is 2x, and that is 2 of the real part of z, which, as we all know, is in the real numbers. Right, so it's important. But there are certain equations where complex numbers show up regularly, and under these circumstances you often end up considering the real or imaginary part. So, you know, it's a simple result, but it's worth remembering. Okay, this is a fun result, and you will, if you continue to study mathematics, and maybe even if you don't, you will see this all over the place. For all z and w, an element of the complex numbers, there's two results here. The first is that the complex conjugate of the sum is the sums of the complex conjugate, and the second result is that the modulus of the sum is less than or equal to the sum of the moduluses. Now this thing here is the triangle identity. Which again comes up all over the place. Proof. Well, the proof for the first bit is easy. Just write it out. And for the second bit, I'm going to say you do it. And you should try it. The best way to consider, to do this is to consider what the square of the sums are, and out what the square of this is. Okay. So, on to section 1.32, subtraction. Okay, so a little bit of a digression. Subtraction can be defined from negation and addition. Or at least if we want the rules that we're going to have to follow kind of our perceived idea. So what I mean is that, if we have x and y in the real numbers, then x minus y is equal to x plus the negative of y. So subtraction is defined by addition and negation. So in order to find subtraction for complex numbers, we only need to know about negation. And negation is not too hard, of course. So, for all z in the complex numbers, z equal to x plus iy, then minus z is equal to minus x minus iy, right? Which is also minus x plus I of minus y, in case that matters. Why? Well, we want, if x is an element of the reals, we know that x plus minus x is equal to 0. And we want the same property for the complex numbers. So we want z plus minus z to be equal to 0. Okay, so if minus z is equal to u plus iv, then z plus minus z is x plus u plus I y plus v. So x plus u has to equal 0, and y plus v has to equal 0, and of course that implies that u equals minus x and v equals minus y. Okay. So now that we have negation, we can do subtraction. For z and w, element of c, if we have z equal to x plus iy, w equal to u plus iv, then z minus w is x minus u plus I y minus v. And everything is as we should expect it. Right, and this is basically the similar result as the one we just saw for addition. For all z an element of c, z minus its complex conjugate is equal to 2 parts times I of the imaginary part of z, and that is an element of IR, pure imaginary. And just for those of you that want to know, this is Ix, or x an element of R. So it's all the real numbers times a complex number. Proof. Basically the same as last time. It's pretty easy. Z plus Iy, complex conjugate of Z minus Iy, and the rest follows. Right, just plug it all in, check it all works. So some examples. 8 plus 2i, minus 3 plus I, 5 plus I. 3 plus 9i minus 5 plus 4i minus 2 minus 5i. Plus. Right. And a nice little diagram. Right, so that's u. Take it off x. And that's v. Take that off y. Oops. Well, think again about vector addition. So, I haven't drawn the angles very well, have I? But anyway, that's meant to be z, and that's meant to be minus w. So, vector addition again. Sorry, it's a bad diagram, badly drawn. Sorry. Okay. So we've got lemma 1.3.8 for all z, w in the complex numbers. Z minus w is the distance between the points x, y, and uv, where x equals z equals x plus iy, and w equals u plus iv. There's z, there's w. So this thing here has got length the modulus of z minus w. And it's worth kind of thinking about that a little bit, exactly why. And my suggestion is you consider the right angle triangle here and you ask, what is that? And what is that? So this is y minus v, and this is x minus u. So Pythagoras, the length of the hypotenuse is y minus v squared plus x minus u squared square root. And of course that is exactly the modulus of the difference of these two things. The modulus of x minus y plus I y minus v. Okay, now we come to the lemma that considers complex conjugation for z and w in C. The complex conjugate of the difference is the difference of the complex conjugates, and the modulus, well, I should probably say the absolute value of the difference of the moduluses is less than or equal to the modulus of the difference. And as before, you can prove these. and it's worth doing this. Just write them out, check the values. Okay. Multiplication. A little more interesting. Right, so for all z equal to x plus iy and w equal to u plus iv inside the complex numbers, w is equal to, I'm just going to write it out and then I will show you why it is defined that way, xu, x times u, plus minus y times v, plus I times xv plus yu. It's a bit arcane, right? So y. Well, it's done like this. Remember multiplying out polynomials? It's the same. So you do this term by term. So x times u, x times iv, iy times u, iy times iv, so that's xu plus I xv plus yu. Okay, so what do we do about this? Well, we've got two i's, and two i's makes minus 1, so it's minus 1 times yv, and the answer is xu minus yv plus I xv plus yu, as claimed. So you treat, just as I've said at the beginning of the lecture, not this one, the first one, the first video, you treat I like a real number, you kind of multiply together and you assume that its square is equal to minus 1, which is where this minus 1 comes from. That's why there's the minus sign there. Okay, so if y equals 0 and v equals 0, then z equals x, w equals u, and zw is equal to, well, there's xu, y is 0, so that term is 0, plus I times xv, well, v is 0, so that's 0, plus yu, y is 0, so that's 0. Right. So this just says same as multiplication in R. So when your complex numbers have no imaginary part, the multiplication that we've defined up here is the same as in the real numbers, which is important because you can consider the real numbers to be inside the complex numbers, and you want to make sure that the complex numbers, the algebraic structure of the complex numbers, also reflects the algebraic structure of the real numbers, which it does. So that's great. Okay. Polar coordinates. Okay, so this is given in the notes as a definition, but it doesn't need to be. You can prove this formula using the Cartesian form of the product, which I've just given you, and the formulas that link Cartesian form to polar form. So z equals r cos theta plus I sine theta. W equals s cos theta plus I s sine theta. ZW equals R cos theta S, that should be a phi. Phi plus I R sine phi S sine, that should be a theta. Theta. Well, I've written them the wrong way around, but it doesn't matter because they're real numbers, so they commute. Anyway, S cos theta cos phi plus I sine theta sine phi sine theta. Now this uses another trig identity. If you don't know it, you can look it up. Otherwise, just take this as the definition. That when you multiply two complex numbers, their arguments add, and their modulus timeses. This is important. Very important. Right. For all Z, W in C. It's basically the same as what you've seen before. The real part of the product is equal to the multiplication of the real parts of these two things minus the imaginary part of Z times the imaginary part of W. And the imaginary part of the product is equal to the real part of Z times the imaginary part of W minus the imaginary part of Z times the real part of W. And the modulus of the product is the product of the moduli. And the principal argument of Z plus the principal argument of W is an argument of Z plus W, but not necessarily principal. Okay, not necessarily principal. You'll see an example of this in the tutorial, but you should think about it. And in particular, I'm going to leave you to do to work through the proof of this. It's not terribly hard. Consider, for example, real part of x, real part of u. The real part of this is the products of the real parts, minus y and v, which are the imaginary parts. So you just write it down. For this one here, just use the definition given in polar form. We know that R and S are the moduli of Z and W, so R and S, the product of R and S is the moduli of Z and W, which is exactly what that says. And this says that the argument's at, which is this. Yep. And you could go about proving these two things using the Cartesian way of writing things down, but it's a lot harder. There's substantially more algebra involved, so you could do it, and I mean you could try it. Just a lot more work, but you would get to know some of the more algebra, and you get more familiar with dealing with manipulations of these things, which if you think could be valuable to you, or you're feeling a little lost and a little confused, then I recommend it. Give it a go. Ask us in the tute. Come visit us in office hours. Yeah. Okay. For all z in the complex numbers, z times its conjugate is equal to 2 times its modulus, which is of course in the real numbers. Proof is pretty easy. z equals x plus iy, the conjugate equals x minus iy, z bar is, well, multiply them out, right? Well, x times x squared, x times minus iy, minus ixy, iy times x, and now here's interesting, we have I times I, which is minus 1, we have a minus 1, which makes 1, and 2 y's. So we get an x squared, that's that bit, we get a y squared, which is that bit, and then the two imaginary parts cancel out, and this is equal to x squared plus y squared squared, all squared, which is the square of the modulus, which is of course in R. Now the proof for this using polar form is pretty good, and perhaps even more direct than this. So you prove it using the polar form. And an example, minus 2 minus I, minus 2 minus I, plus I. Minus 2 times minus 2 is 4. Imaginary parts cancel, so we don't have to worry about that. I times I is minus 1. Minus 1 is in there, so plus 1 equals 5. Check the imaginary parts cancel if you don't believe me. 1.3.17. Okay, for all z and w inside the complex numbers, the conjugate of the product is the product of the conjugates. The notation's not great, right, because there's a very small difference between those two things. So just watch what the line is over or not over, and be careful when you write it out yourself. And the proof, you do it. Again, just write this out. Polar or Cartesian form should follow nicely. Okay, so now we get to some geometry and another diagram, and this is where I justify what I said when I equals rotation. Okay, so thinking about the polar form of these now, because this is much easier to figure out using the polar form. So here you have phi and a line of length r, w, theta, sorry, w is phi, and a line of length s. Then we want to add the two bits on, so let's say it's about there. Then we multiply s and r. So length SR, and the angle is theta plus phi. So multiplication rotates and stretches. Rotates and stretches. Okay, now I is equal to 0 plus 1 times I. The modulus of I is 1. And the argument of I is pi over 2. And you can see this because in this diagram, that's where I lies. So if you consider z, length r, and theta, then, I've done it a bit long, but anyway, iz is theta plus pi over 2. So rotation by 90 degrees. And the length of this line is 1 times r. So multiplication by I is rotation by pi over 2. What's that on? Page 10. Okay. This is a nice example of how complex numbers can capture what would otherwise be awkward geometry. So if Z1 and Z2 are complex numbers, and R is just some number bigger than 0, then Z1, Z2, and Z3, which is equal to Z1 minus IR Z2 divided by 1 minus IR, the 3 points of a right angle triangle. Which I think is pretty cool. So in particular, the diagram here is there's Z1, there's Z2, we have a line between them. So you want to pick Z3, and you use this explicit equation to pick it. And you pick it so that that angle there is a right angle, which I have not drawn well, but anyway. So how do we prove this? Well, we can prove it by showing that the line between Z2 and Z3 is at right angles to the line Z3 to Z1. And this is kind of novel. So let's work out what this line is. Z1 minus Z3. Now, I'm going to leave the algebra to you. It turns out that it is I times some number times Z2 minus Z1 over 1 minus IR. And if we write down Z2 minus Z3, this is Z2 minus Z1 over 1 minus IR. Okay, now, what did I just say about I? Multiplication by I is rotation by 90 degrees. So we have one line, and we have another line. And apart from a bit of stretching in the line, we know that one of them is at 90 degrees to the other one, because the equations are the same except for this multiplication by I. That means that the two lines are at 90 degrees. So this implies that the lines in the plane through Z1 and Z3 and Z2 and Z3 cross at 90 pi over 2 degrees. And the last remaining line is between Z1 and Z2. And so the triangle, whose points are Z1, Z2, and Z3, must be a right-angled triangle. Now, if that's not super clear, if you're a little confused by that, just have a think about it. Mull on it for a while. My experience with mathematics is that it requires substantial mulling, if that's a thing. Sitting, thinking, letting something percolate through your brain. Play with the algebra. You could write out in full Z1. So Z1 represents a point. So use the Cartesian, ordered pairs to represent these things, and actually do the calculation in the plane rather than in the real plane, rather than in the complex plane. Point is that complex numbers make the algebra easier. You get to keep track of both coordinates at the same time, and you get this nice little identity out that multiplying by r is the same thing as rotating by pi over 2. I like that result. I think it's very nice. Just think about it. You know, ask us in the tute. Ask me in the tute about it. Okay, now division. 1.3.4. Now, do you remember what I said about subtraction? That subtraction was defined by addition and negation. It was the same thing. Division is defined by multiplication and inversion. It's the opposite of multiplication. So what we want is, if we have z in the complex numbers, we want the inverse of z, so that z times 1 over z is equal to 1. Now we've seen this, right? We've seen an example. So I times minus I is equal to minus 1 times minus 1, which equals 1. And that implies that minus I is equal to 1 over I. Right? Minus I times I is equal to 1. This also happens to equal I divided by I, which equals 1. So we have minus I times I is equal to I times 1 over I. Let's divide this by I, let's divide that by I. Those i's cancel, and this cancels with that. Minus I equals 1 over I. That's a crude way to say it, because you actually need specific properties in the group to ensure that you're allowed to do division like that. Complex numbers you can, and you do it better by finding things this way. Okay, so what about in general? X plus IY. Oh, sorry, let me do a little geometric argument for the same thing, because this works quite nicely. So another way to think about this is, we have z, we have I, and multiplication iz, that's theta, and we know that this angle is theta plus pi over 2. So we want the element, when you multiply by it, takes back, subtracts off pi over 2. So that element is going to be, and has modulus 1, and takes back pi over 2. So we want the element that is cos minus pi over 2 plus I sine minus pi over 2, right? So we want to take off pi off 2, because when you multiply by 2, multiplying by I is rotation by pi over 2. So if you want to multiply by the inverse of I, you need to rotate by pi over 2 in the opposite direction. The opposite direction and pi over 2. Okay, so what is this equal to? It's 0 plus I times minus 1, as needed. So that's another way to think about it. I can't remember, 13 probably. Okay. So z equal to r cos theta plus I r sine theta, 1 over z is going to be s cos phi plus I s sine phi. Multiply them together because we have the rule about how these multiply. I s cos theta plus phi plus I sine theta plus phi, and we want this to be equal to 1 because we want division to occur, and that implies that rs has to equal 1, which implies that s equals 1 over r, and we need this bit here to be 1 and this bit here to be 0, right? Because there's no imaginary part of 1. So that's 0, and that has to be 1, and the obvious choice in this case is that phi equals minus theta. Right? Just the same way we did it here. Okay, now you can work out a formula using the Cartesian form as well. It's a little more complicated, and we will get there in just a moment. Right. So what is worth noting is that the following is true. Z times 1 over Z, right? R over R times cos sorry, let me rewrite this. Z equal to R cos theta plus I R sine theta. So the complex conjugate of this is, we've proven it before, R cos minus theta plus I R sine minus theta. And this is equal to R squared times 1 over R times cos minus theta plus I sine minus theta. This is equal to R squared of 1 over Z. So in particular, 1 over Z is equal to 1 over R squared of the complex conjugate, and that is of course 1 over the modulus squared times the complex conjugate. And this holds for all Z in the complex numbers, because we've just proven it. So now you have a nice formula. Let's have a look. 1 over I is equal to 1 over the modulus of I squared times the complex conjugate of I. Modulus is 1 minus sign. Inverse is multiple of conjugate, which is a nice little formula. Okay, so now we're going to show you a nice way of keeping track of things and multiplying things out when you're using the Cartesian form. Z equals x plus I y. 1 over Z is equal to 1 over x plus I y. We can times this by x minus I y over x minus I y, and handle this just like fractions, which is a little bit of cheating because I haven't actually shown you that that these things work this way. I'll explain it in a moment, but it is true, and you can prove it. So this times that, x plus I y, x minus I y, because that is the conjugate of that, and we know from earlier on that this ends up being x squared plus y squared, which of course is equal to, as we had before, the conjugate over the modulus squared. Okay, so what was I meaning? This is not fully justified. Haven't shown you absolutely everything to do this, and to be honest, this is the case throughout the notes, that there are points where we've done things that haven't quite been justified. And we're now coming back to proving them, of course, in this section. But anyway, what I mean is we have not shown that 1 over ZW is equal to 1 over Z times 1 over W. You can prove this. What is the left-hand side? What is the right-hand side? Are they equal? And you can do it using the formula 1 over Z is equal to try it out. Again, the more manipulation you do with these things, the more familiar you'll become, the more ingrained it'll be, and I think importantly, the more natural as you do it, you'll see that there is a real consistency here, and it follows from the group theory stuff. Okay, for all z and w in C, z over w is equal to 1 over w squared z. Okay, so what does the proof consist of? It's pretty simple. Z over w is the same as z times 1 over w. We have before that this is z of w bar over, right, which is the proof. Pretty simple. So for all z and w in C, if z is equal to x plus I y and w is equal to u plus iv, then we have some things, 4 facts, which of course are similar to things you've seen before. X u plus uv over u squared plus v squared. And the imaginary part is probably guess, if you look back in your notes at least. Yep. And the modulus of the division is the, predictably, division of the modulus. And arg z, the principal argument of z, minus the principal argument of w, is, as before, only an argument of. And again, you'll see examples of this. Okay, so this has pretty much been proven all before. So I'm actually not going to go through, the direct proof, which is in the notes, and you can look at, or you can sit down and prove it. Instead, what I'm going to do is basically do it by showing you how the previous lemmas can all be put together to show this. Okay, so to start off with, we know that z over w is equal to z times z bar over w squared. Now w, the modulus of w squared, and we know that this is u squared plus v squared from earlier on. So we know that the real part of z over w is equal to the real part of this product divided by u squared plus v squared, because u squared plus v squared is real. So whatever the real part of this is, we'll have a term underneath, so it comes out. And we know what this is from lemma 1.3.13, and that gives us the result. Go check it. Look up lemma 1.3.13 and prove that I'm claiming something reasonable here. Okay, so the same argument, i.e. lemma 1.3.13, and the imaginary part of z w bar over is equal to gives the second result. Okay. Right, and that uses lemma 1.3.13. Uses it twice. Once to be able to split out this bit here, and once to get out the real part. And the step here that uses lemma 1.2.11, look it up, look it up. These are real numbers, so they cancel, just like real numbers always cancel. We get the result out. And stuff to do with the argument follows from lemmas 1.3.19, 1.3.13, and 1.2.11. You do it. What's the point of doing it this way? My point of doing it this way is you build up simple results and you can use it to prove more complicated things without proving it directly. But the direct proof is possible, and you can do it, and it's given in the notes if you want to see it. But you don't need to always calculate everything out. You can sometimes appeal to previous results and say, well, you know what, this step is true. I don't have to calculate it out explicitly. I know that this step is true because I have proven it in a slightly different situation. In any case, the full calculation is in the notes if you want it. Okay, so now we've got an example. 1.3.21. 3 plus 2i divided by minus 2 minus I. 3 plus 2i minus 2 minus I at times 1. 3 plus 2i over minus 2 minus I. And we're going to split this up. Minus 2 plus I over minus 2 plus I. Now we're going to multiply stuff through. So 3 times minus 2 is minus 6. And we have 3 times I plus, we get minus 4i, and then we get minus 2. Oops. Over, and these are complex conjugates timesing each other, so that is 5. So this is minus 8 minus I over 5. Easy. 1.3.22. For all z in W and the complex numbers, the modulus of the division is the division of the moduluses. Proof. You do it. I'm serious, you should do it. It'll help you learn the class, the material, thinking about things, and it also helps with revision. Maths, you have to do maths to learn it. You have to practice math. You can't learn to paint just by looking at paintings, right? I guess. I don't know how to paint, but I assume in order to learn how to paint, you have to paint. But anyway, maths. You have to do math. You have to math to be able to get maths. Yeah, okay, now, section 1.3.5. Okay, I'm not gonna write all of these out. So for if you're watching the video, section 1.3.5 is a list of rules, equations satisfied by the complex numbers. In particular, the rules imply that the complex numbers are what is called a field, which is a very important algebraic structure if you ever spend a bit more time looking at algebraic structures in math. Okay, so some of the rules that are important, the rules make it clear. They restate the fact that addition is needs a negation, or that there exists a negation, and that negation defines the subtraction. Same thing goes for multiplication, inversion, plus division. And now, what is also important is R is also a field. So the elements of R and the elements of C satisfy all the same algebraic properties. Now there is an important difference between C and R, which you might eventually come to see. But the point is that these things are the same. So when I first started lecturing this, I said that you can basically treat I like a real number, and you can throw it around just like you can a real number. In the same way, your intuition is correct. Everything is basically the same. And the fact that C is a field and R is a field is the justification for that. Everything behaves the way you expect. Okay, so some of the rules we haven't talked about. Most of them we have, but some of them you haven't, and so I'm going to write them down. For rule Z, W, and C, inside the complex numbers, we have Z plus W plus C equals Z, W, which basically says it doesn't matter what order you add stuff in, you get the same result. And this says it doesn't matter what order you multiply things in, you get the same result. And these are association. C and R are associative. Okay, Z plus W equals W plus Z. ZW equals WZ. This is called commutation. R and Z are commutative. Last one, Z, W plus C equals ZW plus ZC. So what's that? The product of the sum is the sums of the product. This is called distribution. Which is why in the list of rules given in section 1.3.5 there's a big D next to it. And that is section 1.3. Well done for making it so far.